Hello everyone. Now we will be discussing about the theory of thin films. But before going into that, we have to understand one other idea about reflection of light. So for now I am just considering a line of separation between two medium having two different refractive indices, and let us consider a light wave that is incident on this medium, and let us see that the light is getting reflected obeying the laws of reflection. The thing which we want to discuss now is that whenever light gets reflected from an interface, a phase shift might happen to the reflected light. So this is the incident light and this is the reflected light. If the interface is having a denser medium, or we can say that if the light is getting reflected from a denser medium, the reflected light will have a phase shift of 180 degree. So if there is a phase shift, there will obviously be a path difference also. And how much will be the path difference? We know the formula, that is phase difference equal to 2 pi by lambda into path difference. So for a phase difference of 180 degree, what is 180 degree? 180 degree is pi radian. So when there is a phase difference of pi radian happening, what will be the path difference? The path difference will be lambda by 2 pi into pi radian, and that is lambda by 2. So this is a very important concept which you need to address before going into the theory of thin film. So whenever you see a reflection from a denser surface, you have to take into account this path change. Apart from the normal path difference, or when you are trying to find out the normal path difference, you have to take this path change into picture. So either you can adjust it in the phase difference with the pi radian, or you have to change it in the path difference formula. So before going into the main diagram, let me just draw what is happening in the theory of thin film. So if this is a film, some kind of film, maybe oil or some translucent or transparent medium which has a higher refractive index, and if we have a light ray falling on that, obviously some part of it will get reflected and some part of it will get refracted. And this refracted ray at the bottom surface will again get reflected, and over here again it will get refracted. So this is the only incident ray coming and falling on the thin layer, but this from the same wave, now we are getting one reflected wave and one wave after the refraction process. So we are getting two waves. Now how are these two waves going to interfere? This is the thing which we are going to address in the theory of thin films. Okay, so before going into that, what will be our discussion all about? If we need to know how these two waves are going to interfere, then we should definitely think about their path difference. So when we address the path difference between these two waves, please keep in mind that we should take this additional path change into account, because the light is coming from a rarer medium, and this obviously this will be a denser medium, so this reflection is happening at a denser surface. So in addition to the normal path difference, we have to take the lambda by 2 into account. So now let's go to the main theory of thin film. So this is the layer or the thin layer which we were talking about, and this is the incident ray that is falling onto the top surface of the layer, and one part of it is getting reflected and the other part is getting refracted, and this is obey Snell's law. And what is Snell's law? By Snell's law we can say that sin I by sin R is equal to refractive index of the second medium with respect to the first. So if the outer medium is vacuum or air, we can say that this refractive index is mu. So sin I by sin R equal to mu. So the refraction at this interface will obey Snell's law always, which is very normal. And this refracted ray again undergoes reflection over here, and again this get refracted, and this ray will be parallel to each other. That is simple geometry. So we already discussed that for this reflected ray there will be an additional path change of lambda by 2. And what do you think about the reflection over here? This is not a denser surface, because the first medium is a denser medium and this medium is a rarer medium. So here the adjustment of lambda by 2 need not be done. But for the reflection at this point, we definitely have to consider the path change of lambda by 2. So keeping that apart, let T be the thickness of this layer. So if there is a layer like this, we are deriving two rays from this incident ray, and now these two rays are going to interfere with each other. So how can they interfere? They can either interfere constructively or they may interfere destructively. And how do we find that whether they are interfering constructively or destructively? Either we should know the phase difference between these two, or we should know the path difference between these two. And by looking at the figure, it is pretty much easy to find the path difference between these two light waves. So let us just analyze the path. This is the reflected wave or the first wave, and this is we can call it as the ray after refraction or the second wave. So what is the path of the first wave? It is coming from here, it reaches here, and then it is getting reflected. What about the second wave? It is coming from here, it is getting refracted, goes till here, and then get refracted. So this is the path. So if we are going to find the path difference, we can easily neglect this portion, because from here to here the path covered is same. So we don't have to bother about that. And here I have assumed a perpendicular line, or you can consider it as a plane wavefront which is normal to the direction of propagation. From this line, the path traveled by both these waves will be same. So we can also neglect the path traveled after this perpendicular line and also this line. And the remaining portion can be taken into account for finding out the path difference. So what is the path of the first wave from A to D, and what is the path of the second wave? A to B and B to C. I hope it is clear. So when finding out the path difference, you have to subtract this length from ABC. So you have to subtract AD from ABC. ABC is the longer path of the second ray and AD is the path followed by the first wave. So you can simply write the equation like the path difference delta X can be given as, so first I will just write the length traveled by the second wave minus the length traveled by the first wave. Is it complete? No, because we already discussed that for the first wave there will be an additional path change of lambda by 2. So we have to make that adjustment as well. So this is the path difference which we need to find out. So if we know this quantity, then we can predict whether these two waves will interfere constructively or destructively, because we know what conditions to be substituted for the path difference in order to get the condition of constructive and destructive. If delta x is n lambda, then we will get constructive interference, or delta x is n plus half lambda or n minus half lambda, we will get destructive interference. But before going into that, even if we substitute the condition, can we always measure these things? Or can we always calculate these things, how the light ray is going inside the thin film? No, that is not how we do it. We might know the thickness of the film. We might know the refractive index of the film. So if we can relate this path difference to the thickness of the film and refractive index, this entire procedure will be much more interesting. just by adjusting the thickness, or just by knowing the thickness we can, or just by knowing the refractive index, we can conclude whether a constructive or destructive interference is happening at a certain point. So before going into that, I guess instead of doing in the middle of the derivation, let's just look into some geometrical relationships in the figure. And why I need to do that is, this L2 is nothing but the path traveled by the second wave, that will be equal to AB plus BC. And L1 is the path traveled by the first wave, and that is AD minus lambda by 2. So is this the path which we need to consider to find out the path difference? Are we missing out something? Yes, we are, because we studied the theory of optical path. Here the first ray is traveling through vacuum or air, but the second ray, after traveling through air or vacuum, is entering another medium. So we should be dealing with optical path followed by this light. And how do we find the optical path? It is very simple. In order to find the optical path, you just have to multiply the refractive index with the original path. So AD plus BC is the path traveled by the second wave. So I am multiplying the refractive index of this medium with that path. You also have to multiply the refractive index of this medium with AD, but you need not do it because that refractive index is 1. If it is air or vacuum, then mu value will be 1. So that need not be done. So before going into this derivation, can we somehow link this AB, BC and AD in terms of this thickness? If we can do that, then we can easily work out this thing. So let us just consider this triangle AEB. In the triangle, if this angle is R, then this angle will be R. Also this angle will be R, because angle of incidence will be equal to angle of reflection. And from this triangle AEB, if you take cosine of R, what will be the cosine of R? Adjacent side EB divided by hypotenuse AB. And AB can be written as AB equal to EB by cos R. And what is EB? EB is nothing but the thickness. So T by cos R. Why did I do this? Because now I have AB in terms of the thickness of the film. Similarly, from triangle BEC, I can write cos R equal to, again, EB by BC, or you can write BC as T by cos R. So AB and BC are the same, that is nothing but T by cos R. Let that be there. Substitution we'll do it later. And what about AD? If this angle is I, then this angle will be I, because again angle of incidence equal to angle of reflection. Then this total angle is 90 degree, and this is a perpendicular line which I have drawn, and this angle will be 90 minus I. So 90 minus I, this is 90, so this angle will be I. So if you consider this triangle ADC, from that what you can say? Can you take sine I from that? Sine I will be equal to opposite side, that is AD divided by hypotenuse AC. So AD will be equal to AC sine I. So keeping these things, let me take a fresh page. So the same figure I have over here. So with the relations just being derived, let's again go back to the path difference. Right? Why are we finding the path difference? We are finding the path difference between these waves, so we can predict whether they will interfere constructively or destructively. So what was the path difference? Path difference was AB plus BC into mu. What is that? That is a path optical path traveled by the second wave minus AD, that is the optical path traveled by the first wave, and in addition to that we have to adjust the lambda by 2 due to the phase change due to the reflection at this denser surface. And earlier we know what is AB in terms of thickness. What is AB? AB is T by cos r and BC is T by cos r. So delta X becomes T by cos r plus T by cos r 2T by cos r into mu minus, so we haven't completed the AD part. So what do we know now? AD equal to AC sin I. We know that. Now what about AC? AC can be written as AE plus EC. So AC can be written as AE plus EC into sin I. Alright. Now from this triangle AEB, so I'll just go back to the other figure, so it is much more bigger. From the same triangle AEB, if you take tan R, what is tan R? Opposite side by adjacent side, that is AE by EB. EB is nothing but the thickness, so AE can be written as T tan R. Similarly, from the other triangle, triangle BEC, this distance EC can be similarly written as T tan R. So AE and EC is nothing but T tan R. So AE and EC is T tan R. So T tan R plus T tan R, that is 2 times T tan R into sin I. So before going this value of, before taking this value into this equation, one of them is in terms of R and the other one is in terms of I. So is there some adjustment which we can do so that we can make this term in terms of R? Yes, we know the Snell's law. We applied the Snell's law earlier. We know that sin I by sin R is equal to mu. Then what about sin I? Sin I will be equal to mu times sin R. So sin I can be rewritten as mu times sin R. Okay. Again 2 mu t. This tan R can be written as sin R by cos R into sin R. Operating, we get 2 mu t sin square R by cos R. That is the value of AD. So I'll bring this value of AD. Why did I do all this? We simply knew that we needed AD, but now I converted this AD in terms of thickness and the refractive index, so that the final format will be in terms of these things. So the path difference can be known just by knowing the value of thickness and the refractive index. Alright, now bringing this to our expression of path difference minus 2 mu t sin square R by cos R minus lambda by 2. Then 2 mu t by cos R is common in these two terms. So I can take it out. 2 mu t by cos R into 1 minus sin square R minus lambda by 2. And what is 1 minus sin square R? 1 minus sin square R is cos square R. So 2 mu t into cos square R by cos R minus lambda by 2. So this can be written as 2 mu t cos R minus lambda by 2. This is the expression for path difference, and this expression is known as the cosine law. So what can we do with this now? We know the general condition for constructive and destructive interference of path difference. So we can just substitute them into this equation so that we can arrive at the equation for constructive and destructive interference for the thin film. So for constructive interference to happen, we can substitute the value of delta x, that is n lambda. So 2 mu t cos r minus lambda by 2 equal to delta x. And what is the value of delta x for constructive interference? That is nothing but n lambda. So bringing this to the other side, we'll get 2 mu t cos r equal to n lambda plus lambda by 2, which is nothing but n plus half into lambda. That is the value of 2 mu t cos r. And for destructive interference, two mu t cos r minus lambda by 2 should be equal to n minus half into lambda. Bringing this to the other side, you will get 2 mu t cos r equal to n minus half lambda plus lambda by 2. If you take lambda common, you will get it as n lambda. So this is the condition for destructive interference, and this is the condition for constructive interference. Do you notice any peculiarities? N lambda was corresponding to the constructive interference for path difference, but due to this arrangement, if the value of 2 mu t cos r is n lambda, then these two waves will interfere destructively. Those two waves will cancel out each other. But if the value of 2 mu t cos r will be equal to n plus half times the wavelength, then these will interfere constructively. This is the reason why we see colors in thin films. For example, if you see a soap bubble, if you place the soap bubble in visible light or white light, you can see several colors on the soap bubble. And why might that be happening? You are not seeing white light, but instead of that you are seeing distinct colors. Why is that happening? For example, let's consider the case of destructive interference. At some parts of the soap bubble, for a particular value of lambda, this condition might be true. Which means, for example, we can take red color. For red color, the value of lambda, at some part of the soap bubble, this condition will be satisfied so that the entire red part will undergo destructive interference. So at that part of the soap bubble, we can see the other colors apart from red. So we won't be seeing white light. Instead of white light, we will be seeing the colors apart from red color. So this similar phenomenon can be observed at various places in nature. For example, if you see a layer of oil lying on top of water, you can see this phenomenon over there. You can see the phenomenon of interference in peacock's feathers, on pigeon's neck. At all these places, you are seeing these distinct colors due to these constructive or destructive interferences, or simply the interferences happening between the waves getting reflected from the top part and the bottom part of the thin layer. And these equations are known as, or this major equation is known as the cosine law, and these are the two different conditions of that. I hope this is clear. Thank you.